Topic 4 is elimination. So I'm going to take another look at solving a system of equations. So I have x minus 2y equals 1 and 3x plus 2y equals 11. And when I was in high school, the way they taught me how to solve this is I would take one of these equations and I would solve it for one of the variables. Then I would use that expression. So if I took this equation, I'm going to solve it for x. I'm going to substitute that expression for x into the second equation. And that's going to give me a second equation that only involves y. So I can solve that and find the actual numeric value of y. And then I can go and plug that into my expression in the first equation, and that gives me my value of x. So let's see. I did that. X is equal to 2y plus 1. Then I put the 2y plus 1. I substitute that in to the second equation. I solve for y, and I get y equals 1. And then I plug this y equals 1 back into my first equation, and that gives me x equals 3. So I end up with the point 3, 1, or the vector 3, 1, being the intersection of these two lines. So now let's look at a more technical approach for solving this problem. So now instead of just calling this x, I'm going to put a 1x here. And I'm going to introduce a little bit of terminology. So a pivot is going to be the first non-zero equation in a row that does the elimination. So when I do my substitution, I'm using the first equation to eliminate the x in the second equation. So that's what I mean by the row or the equation. This is the equation that's going to do the elimination. So I'm going to use this equation to eliminate x. And the pivot is going to be the first non-zero. So I'm looking at the coefficients here. The equation that's going to do the elimination is highlighted, and the first non-zero coefficient is this 1. So that's why I had to put a 1 here, just so I could highlight it. So that's going to be called the pivot. And then I'm going to use that pivot to work out a multiplier. So I want to eliminate a number. So if I want this equation to no longer depend on x, then the number I want to eliminate is 3. And my multiplier is just going to be this number that I want to eliminate, divided by the pivot. So in this case, my multiplier would be 3 that I want to eliminate, divided by 1, which is 3. And then if you think about what actually happened when I substituted that expression in for x, so when I substituted x equals 2y plus 1, this is sort of what I was doing. So I was adding negative 3x. And so what I'm going to do is take this negative 3. The 3 is the multiplier I worked out. When I want to eliminate, what I'm going to do is take negative, my multiplier, times the row that's doing my elimination. So that's this first row. And then I'm going to add that to the second equation, so the equation where I'm trying to eliminate a number. And so if you see what happens when I multiply negative 3 times 1x, that's going to give me minus 3x. And then when I add 3 plus negative 3 is going to give me 0x. So that's what I mean by elimination. I'm eliminating the coefficient on the x in the second equation. And then to keep the equality, I have to do the same operation for the rest of the coefficients. So here I'm going to have negative 3 times negative 2. So I'm going to have 2 plus 6. So I have 2y plus 6y gives me 8y. And then I also have to do the same thing to the right-hand side. So here I have 11 plus negative 3 times 1, and that gives me 8. So one elimination step, or sometimes this is also called an elementary step, is just going to be to subtract a multiple of one equation from another. So in this case, I'm subtracting 3 times the first equation from the second equation. And the idea is to use elimination to create something called an upper triangular system. So for a 2x2 system, we achieve that after just doing one elimination. So upper triangular system means that every coefficient below the diagonal, so here you kind of have to imagine there's a matrix, but I have, when the row is equal to the column, that's my diagonal. So 1 and 8 are my diagonal elements. Below the diagonal is just the coefficient on this x in the second equation. And if I can make that 0, then I'm going to call this system an upper triangular system. So it's only coefficients in the upper triangle here that have non-zero coefficients. And if I can do that, then it's going to be really easy to solve for x and y using an algorithm called back substitution. So if a system is upper triangular, then whatever equation's on the bottom, it has zeros in all of the places except for the very last one. So if I look at the bottom, I only ever have to solve this. And so in this case, I have 8y is equal to 8. That gives me y equals 1. And then once I know that y is equal to 1, I can plug that in here. So I'll move all of the y's to this side, and I just end up with another upper triangular system. So this is a trivial upper triangular system because it's just x equals something. But if there are more variables, I'll have to do this one time for sort of each equation. But every time, I have a very simple equation to solve. I only ever have to solve something like that. So I solved for y, then use y to solve. Then use y to solve for x. So I thought I was going to actually do it, but I guess I forgot to. So if I end up with y is equal to y is equal to 1 is going to solve this, and then I'll move this to the other side of the equal sign and plug in my value for y that I just found, and I will have 1x is equal to 1 plus 2, or x is equal to 3. So I get the same solution that I got in the previous slides. And what we're moving towards now is can we represent an elimination using a matrix? So now let's consider a slightly more complicated system. So now I have 3 equations and 3 unknowns, and I want to write that in the form ax equals b. So here's my system. And I can write that in matrix form. So I have A as a coefficient matrix, so you can verify that it just has the same numbers as I have coefficients over here. The unknowns are this vector x, and then the vector b is the right-hand side, so it's the 2, 8, and 10. And just ahead of time, I'll tell you that the solution is -1, 2, 2. And so now if I think about this as a matrix formula, ax equals b, that's both the row form and the column form of the system. And so I can either think of this as just dot product. So if I do the dot product of each row with this solution, we'll see that we get 2, 8, 10. And I can also think of this as multiplying a times x as this linear combination. So it's the first element of x times the first column of A, plus the second element of x times the second column of A, plus the third element of x times the third column of A. And that also gives me 2, 8, 10. So I can represent the original equation as ax equals b, or the original system of equations. And now let's think about what is elimination going to look like in terms of a matrix. So the first thing I want to do, I want to subtract 2 times the first equation from the second. So I want to start eliminating. And so I'll use something called an elimination matrix. So this looks a lot like the identity matrix. It's zeros almost everywhere, except for the main diagonal, which is equal to 1. So if this -2 here were a 0, then I would just have the identity matrix. So mostly it's going to leave my system alone, except here this -2 is going to have the effect of, so it's in the 2, 1 position. So it's in row 2, column 1. And so that's going to subtract whatever this value is. So the multiplier in this case is 2. So it's going to subtract 2 times the first equation from the second. And so we can see that just by using either one of our matrix vector multiplication pictures. So if I multiply, so here I'm just looking at the right-hand side to make the example a little bit easier. So if I have 1, 0, 0, dot b1, b2, b3, that's just going to give me b1. So this matrix leaves the first element unchanged. Then if I say -2, 1, 0 times b2, b1, b2, b3, that's going to give me 1 times b2 minus 2 times b1. So it's subtracting twice whatever was in the first row. So twice whatever was in the first row from the second row. And then 0, 0, 1 is just going to give me b3 back. So that leaves the third row, or the third element, unchanged. And so if I multiply this by 2, 8, 10, this is just me plugging in 2, 8, 10 for b1, b2, b3. That gives me 2, 4, 10. So the identity matrix has 1s down the diagonal. So in general, an elimination matrix that subtracts a multiple, so this is an L right here, a multiple L of row j from row I. It's an identity matrix, except it has an additional non-zero entry equal to minus L, and it's in the ith, jth position. So E31, so this is going to subtract 3 times row 1 from row 3. Is that right? So I want to subtract a multiple of row j. So j is the second index, 3 times row 1 from row I, so from the first index, from row 3. And so this is just the example I did on the previous page. So previously I'd written out the whole form of the matrix. Here I'm just going to say E21. So it's subtracting 2 times row 1, so 2 times this index from this index. And then remember, the identity matrix is just leaving a vector unchanged.